Hello, everybody. I'm honored to be asked to give this talk today. And these are my reflections on Professor Ito. I graduated from his lab in January 20 or 2000, so that's been more than 23 years ago. I'm 52 years old, so that's half my life ago. And my time in Ito's lab really set me up for my career, and it changed my life. My talk today is called Reflections on Professor Ito and the Quasi-Yagi Antenna. This is the overview of the talk. It's going to contain my personal reflections and thoughts about spending time with Professor Ito. I was in his lab from 1996 to 2000. I worked on a variety of topics. I found, Ito was very dynamic, and it was very easy to work on a lot of different things while at UCLA. Different topics I worked on are active antennas, high efficiency power amplifiers, power combining, and finally I worked on the Quasi-Yagi antenna for my work was on array applications, but that's what I'll be talking about as far as the technical portion of my talk today. Uh, I'll conclude with my own personal impressions about Professor Ito. So let me start with this picture. This is my first IMS. It's 1996. I think it's actually 1997. But this is Denver, Colorado. And this is at IMS we do the every year Ito would have a UCLA booth where the graduate students would have to do booth duty. We'd make posters, and there would be a sign up sheet, and we'd all do our time at the booth. And we've got from the left, we've got Yongshi Chen, who was a postdoc. We've got Vesna Radicic, who was a PhD student at that time. I'm third from the left. We've got Kwangping Ma. We've got Al Perkins and Tatsuo Itoh. So this was my first time at IMS, and I didn't have a paper there because I was a very new graduate student. So if you had a paper, Ito would fly you out there. Since I didn't have a paper, I actually drove there from Los Angeles with Al, because Al preferred to drive. So let's talk about what life in Ito's lab was like. That was 4 years of my formative years, and it was collaborative. I think there were students from many different countries. We were all new, and everybody just wanted to get to know each other and know what other people were doing and what people were like. So it was very collaborative, and there were lots of opportunities. I think this is the benefit of working for a dynamic professor. There was as much work as you could do, right? You had to be good enough to do it, but Ito always had work for you. And we collaborated on papers, we collaborated on projects, collaborated on proposals, and even book chapters. I wrote 3 book chapters with Ito. But we worked long hours. I think a little shorter when Ito was out of town, and that's another benefit to having a prominent professor as an advisor. He was gone a lot. But when he was in town, we worked pretty hard. I think Ito would occasionally think we were being lazy graduate students, and he once set up a bulletin board in the lab, and we were supposed to put where we were hour by hour, all hours of the day from 8 a.m. to 7 p.m., which is not very popular. I think the bane of my existence for the 4 years in Ito's lab were the lab meetings, which started at 7 p.m. on Tuesday nights. I still remember that. And they sometimes went till 10 p.m., which I still remember that. This was my first experience going to Los Angeles, being in a big city. I was from Virginia, but everybody was from somewhere, so we all kind of met each other, and we knew that we were all part of the group, part of the lab, and we all got to be good friends. And this was, I mean, for me at least, it was my first significant exposure to other cultures and foods. Another big memory I have of Tatsuo is playing racquetball with him. Uh, he was when he was in town, which was it was probably half to two-thirds of the time. He liked to play racquetball 3 times a week. So I was a young man at this point in time, and Ito told me my night was on Wednesdays, and so I would play him Wednesday every week for racquetball. So Ito was more than twice my age, and I'm tall. I'm 6'1". I like to think I'm in good shape, but he would beat me every single time we played. So he was much more graceful. I think he had much more endurance than I did, and I would get frustrated every time and just play harder. He would not be phased, and he just beat me every single time. A few other stories about Ito. I think but by the time I was in Ito's lab, I guess the rumor is he'd already kind of mellowed with age. And I don't know why this is, but you get stories from how hard he was before. And I know, he would be always working at 8 or 9 o'clock at night if he was in town. And, some of the graduate students would work that late. Some of us would not. Some of us would go home and work from home. But you get the stories about how much harder he was before and how high his expectations were. One of the things which I heard was he used to have an intercom running to the graduate students' offices, and Olga told me this story. And if it was, he would expect you to be there and answer the intercom when you had a question immediately. Another story I heard was when he used to be on travel, he would call at midnight every night, and he'd want to see who was in the lab. He would actually go down the list and he would talk to every single person in the lab just to make sure you're in the lab at midnight. And this would occur night after night. This is not my experience. This was earlier. And I was even told by another alumni that when he was at Austin, if you didn't like what you were saying in the lab meeting, that he would toss the something at you. I mean, this is anecdotal, but I heard he tossed the eraser at a student a few times. Overall, this was not my experience. I thought he was extremely kind and very supportive. He would push us very hard, but I never heard anything other than gentle words from him. So what did I take away from Ito? I think the key thing is to work hard, and I continue to do that, even now in my career. Another thing is to collaborate. I have found that I'm a researcher in industry, and I collaborate with people from all over the United States and even outside the United States. And I've found that by doing that, you can make things much bigger and grow things, and everything gets a lot better. So collaboration is a really, really important thing. Now, one of the other things is, as much as I complain about the weekly lab meetings, they were useful. We all learned how to present technical ideas, and that's helped me immensely in my career, and I think it helped the other students as well. Another thing which I saw is in conferences. A few times, believe it or not, in some sessions, I would see professors would actually ask pretty cutting and critical questions of student presenters, and Ito never did that. He would always be gracious and supportive, and we used to talk about that, how the right way to behave in conferences is to be respectful of everybody's ideas. So let me talk about the Quasi-Yagi antenna a little bit, and you'll see why I'm talking about this a few slides from now. But it's it's an antenna that was developed in Ito's lab in the 90s, and several people contributed to it. I think the student who really probably should be able to claim the person that he invented it was Noriaki Kaneda, who I think graduated a little bit after I did. He was a great guy. And then there was Dr. Yongshi Chen, who was involved with everything and was very energetic. Had written a book on FDTD and was supportive of everything. My role in this, I didn't invent the antenna, but I thought the antenna was pretty cool, and I tried to apply it to array applications and different circuit applications, which I'll talk about a few slides from now. And this shows the antenna. So the Quasi-Yagi antenna, right? The Yagi antenna is a dipole antenna. It's got multiple wires, including a it's got the element itself. It's got the reflector, and it's got at least one director. It's got, I mean, the wire inversion has multiple directors. And in this picture, it's a microstrip version, and so there's a microstrip feed from the bottom. There's a balun, which consists of a splitter and a coupled line. And then there's this coplanar strip line, which truncates. Well, it goes across the ground plane, but it goes to the dipole. And there's a truncated microstrip ground plane. So the microstrip ground plane acts as the reflector. Of course, the dipole antenna itself is the main element. And we have one director in this particular antenna. And it's pretty unique in the sense that it's fabricated on a high permittivity substrate, which makes it electrically very, very small. And to depict that, there's a photo on the right of the antenna fabricated on it's a Rogers substrate. I forget what it is, 11.6 permittivity or something, and it's shown on a quarter, so it's pretty small. It ends up being end fire, just like the classic Yagi-Uda antenna, but it's got broad bandwidth, I think 30% bandwidth or so. Unlike the Yagi-Uda, it's got moderate bandwidth. This particular version has probably got 3 to 5 dB gain. And this just shows the radiation pattern, so you can see the low gain, and it shows the measured bandwidth for this version, which is pretty broad band. The 10 dB bandwidth is from 7.4 or so up to 11 point something. So that's very broad bandwidth. My primary interest in this, right, I had seen they had a lot of work going on in imaging at that point in time. Passive microwave imaging using Vivaldi antennas, and the Vivaldi antennas were pretty big. I saw this as a very unique antenna for doing these card-based arrays, which I thought would be superior to the Vivaldi. And I did a variety of works with this. You see one right here where we've got a 1x8 card with antennas on it. And we did up to 64 element arrays just to show that this was a useful array element in 2D arrays for these kind of card-based arrays. There were some things you can't see it from this photo, but one of the things that started happening when we stacked these cards is you started getting a big reverse array. So the previous chart, you had a good front to back ratio. But once we stack these things, you actually got almost equal backward reflections, and we had to do some tricks to get the wave in the forward direction, which we were successful with. But it's an interesting antenna. Here's another work by Noriaki. You can see I'm not a co-author on this, so this was done. I think this was actually done while I was still in the lab, but I don't remember it. And Noriaki applied this antenna to a coplanar waveguide to waveguide transition, and you can see he's got a back-to-back transition on the left, which sits inside the waveguide, and the waveguide is kind of cocked sideways, but the electric plane of the E field. The electric field of the antenna is aligned with the electric field of the waveguide, and it ostensibly transitions from coplanar waveguide to waveguide mode. So this actually became a very important work for me, and this shows a photograph where I've taken that idea and I've applied it to an integrated circuit. This is an indium phosphide circuit. I'm showing on the right here, you can see a 670 gigahertz low noise amplifier. And we're using almost identically the technique which Noriaki proposed. And this integrated circuit is mounted, on a pedestal, just as it shows on the prior chart. and you've got a dipole antenna which couples to the waveguide at the left and the right. And this is a high gain LNA, which works very well. The reason we use this rather than an E-plane probe, well, two reasons we use this. The first thing is that you can't really do RF wire bonds at 670 gigahertz, so you have to find some other way to do it. We worked a bit with trying to do E-plane probes on integrated circuits, and what we found was that the substrate modes were quite bad. But using the Quasi-Yagi antenna, the way it's oriented in the waveguide, we found that we could suppress resonances and get almost full waveguide bandwidth on this high permittivity substrate. So it's pretty attractive what we were doing. And we've in fact done it up to 1.1 terahertz. Now, so I use that antenna on the prior chart, almost every day for packaging parts. I've been lucky that I've been able to do that for more than a decade. One of the questions I always have is, we've published papers on it, but does anybody actually use this antenna? And I don't know the truth. I don't know if it's used in wireless. I don't know these things, but I do know that a lot of people work on the antenna. And this is just doing a quick Google search and looking at images and doing a screenshot of the top of the page. You can see, lots and lots of different variations of it. And, I have probably 12 or 1,300 citations for the papers I published while at UCLA. And so I know it's an active topic at least. But then, okay, so people still work on it, but is it useful? And I still don't know the truth of that either, but at least people patent it quite a bit. And this shows, doing a Google patent search for Quasi-Yagi antenna, you get 3,800 results come up, and these are the results from the top page, which shows, at least a few results, or probably not a few, many results. All right, so let's transition a little bit. So this is what I learned about research from Itoh, and for life. I think the number one thing is to collaborate. When you try to help other people, what you find is that other people try to help you, and that it helps what you're doing, and things grow, right? You can make something much, much larger than what you can do for yourself. I think another important thing is to try to recognize other people's work. I'm old enough now that probably less competitive than I used to be when I was younger, but it's good to build bridges, and it's good to honor people and respect what other people do. And it's good to be gracious. I think just from conferences, when you see young students presenting, they're probably very scared. It's good to try to listen to them. Try to hear them and try to help them as you can. And then as far as work, Itoh was a prolific author. I'm not as prolific, although I like to think that I'm fairly prolific. I think it's important to take each thread of research as far as it can take you, and you'll find lots and lots of offshoots. And then probably the most important thing is to work hard, because everybody's going to appreciate that, and it'll keep bringing in funding and keep bringing in ideas and other people to collaborate with. All right, and so this is my conclusions. It's I want to thank Itoh for what he did for me, and thank him for what he did for all the other PhD students and master's students, all the other people that he touched. He's had a significant impact on the world through his research, just tens of thousands of citations. But for me at least, more importantly, he's touched my life. He's helped my career, and I think he's helped the careers of many, many other people. Anyways, I want to thank you for your time, and I want everybody to hopefully go think about Tatsuo tonight, and and we should all try to emulate him in our life and our careers. Thank you very much.